Okay, cool. I'm gonna start with number one. I didn't write down assumptions for some reason when I did this in the exam, but for number one, the assumptions start by using ideal gases, adiabatic nozzle, isentropic flow, and there's a constant heat capacity ratio, and it's steady, uniform flow. Gamma is 1.15. I converted the megapascals to pascals for P critical, and then T critical, I converted that to Kelvin. And the Mach number I just pulled from above. But I used the normal gas constant and divided that by the molecular weight to plug into equation later, and that got me 2.73 times 10 to the second joules per kilogram Kelvin. And we need to find the exit area, and so that's pi diameter of the exit squared divided by 4, and that's 6.65 times 10 to the negative 1. Need to find the t exit, and we're pulling that formula off of one of the handouts, and that's t naught over 1 plus gamma minus 2 multiplied by the Mach number squared. And that's 1.95 times 10 to the third Kelvin. Then we need to find the exiting pressure, and by manipulating this equation also from the table, you can get P naught times T exiting over T naught to gamma divided by gamma minus 1, and that gets you 7.7 times 10 to the fourth pascals. And you find the exiting density, which I just used the ideal gas law and manipulate that around using the R that I found above, and that's 1.44 times 10 to the negative 1 kilograms per meters cubed. And then from there, you can find the velocity. I split that in two different parts so it'd be easier in my brain. But that's 2.68 times 10 to the third. And then from there, you can plug in the density of the exiting, the velocity exiting, and the cross-sectional area exiting. Multiply that together to get m dot, which is what we're looking for. And then that's 2.6 times 10 squared kilograms per second. I did that part right both times. So we're just going to go past that. For number two, the value of the drag coefficient for a streamlined body is 0.04, and that's from table 11.2, which applies as long as the Reynolds number is turbulent, not laminar. And you can find the Reynolds number, which is rho VD over mu, and that's 2.3 times 10 to the seventh, which is turbulent. And from there, you can solve. You have to convert the velocity from kilometers per hour to meters per second, which is 401.1 meters per second. And then from there, you can plug into the cross-sectional area, which is again pi d squared over 4, which is 0.665 meters squared. And then the drag force is 1/2 rho v squared times the drag coefficient times the cross-sectional area. And that gets you 7.92 kilonewtons. I did the first part of that right then. So anyways, I did do part A correct when walkthrough anyways. The ratio is the out, the very last outlet pressure divided by the very first one, and then it's all to the power of 1 over the number of stages you have. You can multiply that ratio through all of the different pressures to get the outlet of each different stage. In that, you end up getting 29.1 atmospheres. B, I did not do that correctly. But I calculated the change in temperature first to make it easier to solve this later, but it's 108 Kelvin. And you need to start by finding the temperature that's going out. So you multiply the temperature going in by P out over P in, all to the power of gamma minus 1 over gamma. That gets you 411 Kelvin. And then there's two different work that we're solving for. We're working for the four-stage process, and then we're solving for the specifically isothermal one. But for just the fourth stage, you're multiplying 4 because there's 4 stages times Cp over the change in T that calculated over there, and that's 13.7 kilojoules per mole. And for the isothermal one, it's RT ln P stage 5 minus P of stage 1, and that ends up getting you 11.5 kilojoules per mole. And on a physical basis, why it takes more work to compare a gas adiabatically instead of isothermally, it's because no heat is removed in adiabatic compression. So all the shaft work goes into increasing the internal energy of the gas, and the temperature has to rise, and that creates, you have to use more. If the temperature is higher, there's more pressure. And so more work is required to get the same thing done. Isothermal compression removes heat, so it's a constant temperature. So the average pressure and in turn work is lower. And then for number 4, I started by converting the flow from liters per minute to 7.83 times 10 to the 5th meters cubed per second. And I calculated the Reynolds number, and that is 1.6 times 10 to the 3rd, which therefore is, remember, you need a cross-sectional area, which is 1.32 times 10 to the 3rd meters squared. And then you divide the flow rate from up there divided by the area in order to get the velocity, and that's 5.93 times 10 to the negative 2 meters per second. And you need your friction coefficient using Fanning's, which is 16 divided by the Reynolds number. I found over there, and that's 1.0 times 10 to the negative 2. And then you're solving Bernoulli's to solve for the pipe head loss, and that's for friction coefficient times L over D, all multiplied by velocity squared over 2g, and that's the acceleration of gravity. But that ends up getting you 3.4 times 10 to the negative 3 meters. I didn't end up finishing solving this one, which is why we're doing it again. For B, you're just pulling that number off the table. I don't know, I'm starting with that. I shouldn't start with that. Anyways, I converted 80 kPa to just pascals, and we're assuming it's a large open tank, no friction. So then NPSH available is the P at suction point divided by PV over rho G. And you can simplify that down since you have the different heights of the surface and pump themselves. That's P atmosphere divided by rho G plus the Z to surface minus the Z of the pump. And you subtract that by PV over rho G. And that ends up getting you 6.78 meters of available NPSH. And so, yeah, you pull the NPSHR off of the graph that it shows you here. But the pump is not likely to cavitate because the NPSHA is greater than the NPSHR, which I got that right down here, but I didn't solve for the available correctly. I did solve for permeability correctly, but just to go through it, in case I need to get the points for it, but Vs is K over mu times change of P, pressure divided by length. And if you solve that for the bed permeability and simplify that down, bear in mind that Darcy is 0.986 times 10 to the negative 12 meters squared, you get 54.646 decibels. And last but not least, we have 5. I pulled most of these numbers off the tables correctly. It's table 8-4. But the assumptions are steady incompressible. It's a Newtonian fluid. Both pressure inlet and the pressure at the outlet are open to atmosphere. And we can assume V1 equals V2 is basically 0 because it's large reservoirs and it's open to the atmosphere for both those assumptions I said. But you can convert flow from, again, meters per minute to meters cubed per second, which is 0.92 times 10 to the negative 3 meters cubed per second. And you also have to pull these values off the table, the density and viscosity of water. but you needed the cross-sectional area, which is pi d squared divided by 4, as a 5.03 times 10 to the negative 3 meters squared. You need the velocity, which is taking the flow divided by the cross-sectional area, which is 1.57 meters squared. You can solve for the Reynolds number again, which is 8.3 times 10 to the fourth. We're making sure that is in fact turbulent. Using the chart and from graph 6.2 in the handout thingamajig, you can find more or less it's the friction coefficient, not the friction factor is 0.025. And using Bernoulli's, you can simplify this down again to find the head loss, which is the friction factor multiplied by L over D times V squared over 2G. And then you add that to the sum of all of the K values that you had to pull from up here, of all the different stuff you had. You multiply that by V squared divided by 2G. And subbing all of that in, you get 3.7 meters. I did not solve Bernoulli properly over here, which is why I didn't. Yay!